Well, as you probably know, I lied in my last video. I was like, let's keep this one under 5 minutes. Nah, that's probably not going to happen. But instead of having 3 more videos, you only have this one and 1 more. So let's get it. Let's put everything together. There's our derivative for parametric curves, right? Derivative on y with respect to t, derivative on x with respect to t. We just divide those two. So here we go. Here's a problem. Let's put some trig in there. So we're going to want to sketch the curve, which means let's parameterize this. Let's get it, or deparameterize it. I don't think that's a term, but it means get rid of all the gosh darn t's. Then let's find a derivative. And then we'll figure out where it's vertical and horizontal. But I think we're sketching the curve so we can see part 3. So let's parameterize this thing. So we're not doing this necessarily in any order. We just want to make certain that we know. Well, actually, we are going to start with changing it up. So we're going to say x is equal to 4 cosine of t. And you remember that trick, right? You remember that trick from before? That trig functions don't work quite the same way. Well, what we want to do here is we want to get rid of the numbers that are attached. So we can say x over 4 is equal to cosine of t. And we can say y over 16 is equal to sine of t. And then we can play that game. X squared plus y squared is equal to 1. Or, oh, no. Cosine squared plus sine squared is equal to 1. So let's take our squares and do one of these. You're like, oh, let's just replace where sine is, and let's replace with cosine. So x over 4 and y over 16. Wow, those are some giant numbers, but it's all good. Do you recognize it? Do you recognize it? Do you recognize it? X squared over 16 plus y squared over, oh, what the heck is 16 squared? 256. Got it. Have you ever dealt with an ellipse before? Because this is an ellipse. You know how to graph those things? It's actually kind of best to leave it like this. See the 4? So on your x values, you go 4 and 4. Or 4 and negative 4. On your y values, oh, by the way, x squared over a squared plus y squared over b squared equals 1 is the form of an ellipse. And so we look at our a, it's under the x, so that's where we're going to go. For our b is 16. We're going to go up to 16 and down to negative 16. And then it just becomes a little ellipse. Sorry, I don't draw well. You already know that. Well, ellipse, like a football or something, being ready to be kicked off. And since both the cosine and the sine, I want to explain why we're going in this direction. So there's our curve. So can you see that the slope of the tangent line might be different for different points? It's not just a line. You can also see where we're going to have the slope of the tangent line equaling 0, right? Horizontal slopes of tangent lines. That'll be at when x is equal to 0. Oh. And then we're also going to see where the slopes of the tangent lines are vertical. I'm going to make a bigger dot for that one. They're at these endpoints. So now we're kind of putting it all together. But this question asks you to sketch it. We sketched it. Cool. Most of the time it's not going to ask you that. It's just going to be like, all right, we'll figure out the derivative. Figure out where it's vertical and horizontal. You don't have to sketch it if you don't want to, but I wanted to make certain that you can see why all this stuff is going to occur. So, all right, so we did number 1. We sketched ourselves a curve. Goes around in an elliptical fashion, kind of like, I don't know, this has no applications, right? Nothing moves in an elliptical way. Or that might be the entire freaking universe. So there are applications to this. We could think of that as maybe how we go around the sun. All right, I should stop talking now because I don't know enough and I don't want to pretend that I do. So we're going to find dy dx next. So we can find the slope of the tangent line for any value of t in between 0 and 2 pi from the beginning, right? Between 0 and 2 pi. Neat. So we're going to need to take a derivative on our g, the y value up top. So that's 16 cosine of t. And then we got to take a derivative down below on 4 cosine of t. That's negative 4 sine of t. So it looks like our dy dx is actually equal 16 divided, that's -4, and cosine over sine, that's cotangent. All right, cool. We found a derivative. Plug in any value of t, it's -4 times cotangent of however much time has passed. Well, crap. Well, how are we supposed to set that thing equal to 0? How are we supposed to solve for cotangent? Solve it up here. So, horizontal means dy dx is equal to 0 over some freaking number. It's equal to 0. Where does cosine equal 0? You just state it. At pi over 2 and 3 pi over 2. That's where cosine equals 0. For it to be vertical, dy dx is undefined, aka 0, and then some number up top. So where does sine equal 0? So this is for our horizontal. And then for our vertical, where the slope of the tangent line is undefined, we're going to find it's at t equals 0 and pi. Are you starting to see something here? That this is just the frickin' unit circle? Except it's not a circle, it's the unit ellipse. Oh, I got to add in 2 pi. It included it. Does that kind of make sense? That it would be vertical at pi and at 2 pi? It'd be horizontal at pi over 2 and 3 pi over 2. There we are. There we are. So we sketched it. We know a little bit about it. We know where it's vertical tangent lines, horizontal tangent lines. We have a derivative for any value you wanted. So if you wanted to look at, pi over 6. Oh my goodness. It's like all this stuff is tied together. It is. That's why you learn this stuff in trigonometry if your teacher's good. Not like me and actually gets to it, so you can do stuff with it. But this is highly useful. Highly, highly, highly useful. All right, we're going to do one more video after this. This is just going to be arc lengths. And then we're done. All right, see you.